Hey guys, going through basic redox reactions. This is not the complex redox. We'll look at complex redox a little bit more tomorrow. But this is just kind of going through what we went through today in class, which is just basic redox. Do we understand what oxidation means? Do we understand what reduction means? Can we write half reactions? That type of stuff. So just understanding what redox means. Redox is the abbreviated term to basically oxidation reduction reactions, which means electrons are transferring electrons back and forth between different elements. Oxidation is the process of losing electrons. This is when your oxidation state is going to become more positive. Reduction is the process of gaining electrons. It's when your oxidation number becomes more negative, hence the reason reduction becoming more negative, it's being reduced. I always remember it with one of two sayings. Personally, I like Leo the Lion says GR, lose electrons is oxidation, gain electrons reduction. Oil rig is another one. Oxidation is losing, reduction is gaining. It's up to you which one you decide to use. I would always have it written in the top hand of my corner of my paper as I'm working on these types of problems, but that's just me. Okay. When we're doing these, first off, we need to understand that all synthesis, decomposition, combustion, single replacement reactions are all considered redox reactions because they are oxidizing or reducing. This is just an example. Water is formed by hydrogen and oxygen. Some things we need to keep in mind is all elements have an oxidation number of 0. So in this case, if we were going to assign oxidation numbers, I'll write them in red here. Hydrogen would have 0, and oxygen would have 0. Okay. In compounds, oxygen is always a -2 unless that compound, let's move this up a little bit so you can see that, is a peroxide. In this case, this is not a peroxide. Peroxide is a polyatomic ion, O2, -2, which we don't use a lot anyways. So in this case, oxygen would have a -2 oxidation number. Hydrogen, in this case, is going to have a +1. And that can be calculated by just looking at the fact that this compound, water, is neutral, meaning all the charges or all the oxidation numbers have to add up to equal 0. Oxygen is -2 because of our rule. There's 2 hydrogens canceling out that -2, so each hydrogen must be a +1. From there, what we do is write our half reaction. So our first step is to write our hydrogen half reaction, which is H2 forming hydrogen. I have already balanced it here by putting the 2 here to balance this. Remember not to pull the 2 up if it's part of the elemental form. So our diatomics we're going to leave as H2. And then of course we have our hydrogen ion. We have 2 of them. Again, same thing here. O2 diatomic, I'm leaving it as O2. It is forming an oxide ion, O-2, and I need 2 of them to balance my O2 over on this side of the reaction. From there, we balance our electrons. So really, our first step is to balance the atoms, which here is already done. If those 2's weren't there, I would have to add those 2. The next step is to balance our charges, and we do that through electrons. So what I do is I see, okay, hydrogen's a 0, and we've already done this, but I'll go back up here and write those oxidation states up here so we see them again. Hydrogen's a 0, and hydrogen's a +1 here. Well, to go from 0 to +1, it had to lose electrons, and technically it lost 2 because there's 2 +1s. So we would have 2 electrons on our product side. It's losing electrons, meaning it's breaking away from or decomposing, if you want to think of it that way, which means our electrons are always going to be on our product side. They're being lost or taken away from. Here we have 0 going to -2, which means it's gained electrons, and actually 2 -2s, so it's actually gained 4 electrons. So that's kind of what we see down here. Now we label them as either oxidation or reduction, and we do that by knowing Leo said GR or oil rig, whichever one you want to use. Okay, so Leo says losing electrons is oxidation. Well, here is where I'm losing electrons, so it is my oxidation half reaction. Gaining electrons is reduction. Well, here's where I'm gaining electrons. It's being added in as a reactant to form a product. So it is a reduction. So that's kind of our first step. Our first step is to balance our atoms. Second step is to balance with electrons. And then, of course, I would always label oxidation reduction because that's typically what we need to know with this. Continuing on. Nope, not continuing on. Let's go back. Continuing on down this way. Sorry about that. I had a little confused in my head. We have it separated. We do all that stuff. We then balance the electrons. The way we do that is we want the electrons to equal each other. So because I have 2 electrons here and 4 electrons here, I need to multiply this top reaction, the oxidation half reaction, by 2. So I end up with 2 hydrogen atoms forming 4 electrons, or 2 hydrogen element atoms, I should say, and then 4 hydrogen ions. Okay, at that point in time, when I add them together, which is my next step, I end up canceling out my electrons because they're on both sides of the equal sign, or the arrow, if you will. And so if I rewrite it, I have 2H2, 1O2, forming 4 hydrogen ions and 2 oxide ions. And of course, when you simplify this further to form water, it's 2H2O on the product side. And again, this is exactly how we would balance it. Yes, oxidation reduction is just a fancy way to balance. Okay, so let's look at another practice problem here. We have a piece of calcium metal is oxidized by adding it to a solution of copper 2 chloride. So our first step here is to write out our reaction. We have calcium metal, which is a solid, plus copper 2 chloride. Okay, this is a single replacement reaction. Calcium is going to kick out copper because there are 2 metals, so we'll end up with calcium chloride. And let's make that more of a definitive A so we know it's not a U, plus copper. Okay, and this is going to be aqueous because it's in a solution. This is going to be aqueous as well because halides are always aqueous unless there was silver, mercury, or lead. And then copper here is the metal, so it's going to be a solid. So from there we can write our net ionic equation, which is going to be calcium plus copper plus 2, forming calcium plus 2 and copper metal. So that is what we're looking at for our net ionic equation. The only thing that's going to cancel out is our chlorine. So from there we write our half reactions, which is going to be calcium, forming calcium plus 2 ions, copper plus 2, forming copper ions. And notice I'm leaving them on the correct side of the arrows where they always were. Calcium is forming calcium plus 2. So my calcium element is still on my reactant side, my calcium ion is on my product side. Same with my copper. Copper ions on the reactant side, copper metals on my product side. So that's staying exactly the same. So my first step after I have my half reactions is to balance my elements. They're already balanced. So the next step is to balance my electrons. So I'm going from a 0 state because I have an element to, sorry about that, to the ion state, which is plus 2. So 0 to plus 2 means we lost 2 electrons. Going from a plus 2 to a 0 means we gained 2 electrons. Okay, so if we wanted to label this, again, we have our Leo the Lion says GERD. So we lost electrons here, so this is our oxidation. Gained electrons here, this is our reduction. Once we have this, we balance our electrons, and they already are balanced, so that's kind of the nice thing. Sorry, guys. So all we have to do is cancel these, and then we can add them together from there. So in this case, our reaction actually ends up being the same as our original reaction, which is calcium plus copper plus 2, forming calcium ions and copper metal. Now, that's not always the case. We saw that in class. But again, this is just a review to get a little bit better grip on redox if we need it.